All right. So today we're going to be doing day 5 of the Advent of Code challenge. And today's problem is that we want to have a safety manual, but we want to print it in a specific order. So the file that we get with all of the input is consisting of two numbers separated by this. And it says, okay, this means that page 47 should be printed before page 53. Page 97 should be printed before page 13, and so on and so on and so on. So there's a lot of rules that we have to adhere by. And then after, it tells us, okay, each line tells us what pages have to be printed. So they want to print this one first, then that one, then that one, then that one, then that one. And we have to check, based on the rules, can we print the page 75 first before all of these pages? And in this case, it is possible because there are these rules here. So 75, 47, 75, 61, which means that 75 comes before 47, before 61, before 53, before 59. And those are all the numbers remaining. So we know for sure that we can print the number 75 first. And then we have to check it for the rest of the numbers. So the next number, 47, is it possible to print it before the other numbers? Yes, because we have these rules here. Is it possible to print 61, and so on and so forth? So there is two parts of in the input file that we get. So it can be a bit confusing. If we scroll all the way down, here's where the second part comes in. And this is the order that they want us to have it in. But if we take the input file, if we take the input file and we put it, we can see it's like how many rules? How many lines? About 1,100 lines of rules, and then about maybe 200 lines of different manuals with pages that we would need to print. So what we would have to do is, let's see if I can draw here. Can I make the size a bit thicker? So we want to parse these rules, and then we also want to parse the different pages that they tell us to print. So the first function that we can make is a parsing function that parses the data correctly. And there's one little hint that can help us. And if we go right here, we see that there's a empty space right here, which is nice. So we can use that to our advantage. So I've made a parse function, which takes the file path. And of course, for the solution, we just take the file path where I put the input.txt file. And then we give the file path to parse. Which will give us two different parts, right? The updates and the rules. So the updates are these things here on the bottom, and then the rules are these things on the top. So we want to somehow split it, and then we want to give it to a solve function that makes sure that we can solve it and print the pages in order, and then we just want to print the result. So this is how we can solve it. So now we just need to make the parse and the solve functions. So if we go in the parse function, what I've done is I've opened the file, I read it, and I strip it in case there's any weird characters or new lines. And then we can use the .split function, and we search for 2\n, which is the symbol for a new line character. So here there's a new line character to go to the from line 1176 to 77, and then from 77 to 78. So there's two new line characters which we can search for. If we search for just one, it's going to give us the result for every line, because every line has a new line character to become a new line. Even though we can't see the \n here, when we see that it becomes a new line, there's an invisible \n there. And that's just how it's rendered to us. Then I've made a rules list of tuples of integers. Sounds a bit confusing, but it is just a list in the beginning. And since the rules are two different parts, so there's a left part and a right part, then what we're doing is we're just splitting it by this character, and we're adding the x part to the left and the y part to the right. And then I'm converting them to integers. So if I can draw again, then what we're going to have here is we're going to have a tuple. So it's going to have the x and y, and then it's going to have more of them, more x's, more y's, and then a bunch of these, and a lot of them. So there's going to be a huge list with more things inside, which is going to be the x's and the y's. So once we append this to all of the rules, this is just for formatting. We have to do the exact same thing for the updates, but for the updates, we don't need to make a tuple because we can just add it directly to the list since it's one thing per index in the list. So there's going to be the 97 in the index 0, 58 in the index 1, 11 for the index 2, and so on and so forth. So we just add them line by line, we append them, and then what we want to return for the parse function is the rules and updates. So this is what we're going to return, and we're going to give it to the sol function, which is right here. So if we look at the sol function, there's a total, which we will have to calculate later. And I'll talk about it in a second. But now, for each update and updates, so for each number in this update here, so the first page that we would like to print is 97, and then 58, and then 11, and so on and so forth. For each of them, we have to check, okay, is it possible to print it first? But before we do that, I would actually like to do this thing here, which pre-computes the indices for each update, because we were going to use them later over here. And it just helps because when we try to search it, we're going to have a constant time lookup instead of O of P, so how many pages there are lookup, or O of N, whatever you want to call it. So it's just a lot faster to do it this way. So the reason that this is faster is because if I can draw this here, so originally, let's say that this is our list with indexes here. So we have index 0, index 1, index 2, index 3, index 4, and so on and so forth. And let's say that we have the number 7 here, we have the number 9 here, and the number 5. It's not very visible, I know, but 7, 9, and 5. And if we want to find number 5, okay, then we're going to have to iterate, and in the worst case, over the entire list, to be able to find number 5, and then, or over the entire dictionary, or what we're using, to be able to find this number. And instead, what we can do is we can sort of reverse it. So we say, okay, we make the same thing, but instead we're going to have, so at index 5, so over here we can see that we take the page indices, which should be a dictionary, and then at the page, so what is the page? In this case, let's say that we start with 7, because this is the first one, then we go at page 7, so 0, 1, 2, 3, 4, 5, 6, this is 7 right here. And at page 7, we will write what index it is. So it is index 0. And then we continue. We add one index every time we iterate. So we're going to be at this page, at page 9. So let's say that 9 is here, and it will have index 1, page 5, 1, 2, 3, 4, 5. So page 5 will be here. It will have index 2. And eventually, it will populate most of this. So for each page, this right now is a page, P-A-G-E, and this right here is an index. So now when we will look here, when we iterate for X and Y in rules, so when we look for each of the rules for 73 and 46, for example, instead of looking and iterating through the entire thing here to look, okay, is there a 76 and a 46 in here? We have to iterate through the entire length of this line to be able to find it. Instead, what we can say is we just say page indices X, which is page indices, for example, 89, and it's going to give us the exact index where it's at. So then we have the exact index, and what we want to do, since we want to know if it's possible for them to be in order, is we just want to compare, okay, is this index bigger than that index? So if the index of 73 and 39, let's say 73 ends up, we have an answer for 73 here, and the index is 0, and we say that we have 43 here, and the index happens to be 5. So we get the indexes for both of them, which is constant time, and then they return 0 and 5, and then we see that 0 is bigger than 5 in this example. So that's a problem, because it means that the rule has been violated. So it is not valid anymore. And then we just break directly, because if any of the rules break, then we have to break directly. So we iterate through all of these that do have the numbers that we are requiring here, the pages that we are requiring. And if all of the rules did not break, then it means that it's still valid, which is great. So what we will do is we will try to find the middle page. And how we can do this, if I can just delete everything and start over, how we can do this is if we have an array of, let's say, 5. So we have 0, 1, 2, 3, 4. But technically it has 5 spaces, right? And then what we do is we do 5 floor division 2. And what it's going to give us is 2 with a remainder of 1. So if we do percentage 2, then it's going to give us the remainder, which is 1. But we don't want that. So we just want this. So this 2 means that we go at index 2, and this should be the middle value. If the array has 4 instead, then 4 floor division 2 is also 2. So it's going to give us 0, 1, 2 to this index. So what this means is just that we're not going to get, I mean, it's impossible to get the exact middle because it's split in 2. So we're just going to get the one that's on the right. And I mean, that's okay. Apparently, this is what they want us to do. They didn't specify what they wanted us to do in the question, like in case that there isn't an odd amount, but all the examples are odd. So I'm assuming that all the examples in the input file are odd as well. But either way, it worked. We got the right solution. But if it's not right, then maybe they just want us to select the left one. So then we would just do another if statement. Okay, if it is even, then select the one that's on the left. And what we do is, since we know what the middle page is in the update, then we just plus equal to it to the total, because that's what they want us to do. So once we find that, okay, this is valid based on all the rules, what they want us to do is, okay, look for the middle value. So find the middle value over here. And in this case, it's this one. In this case, it's this one. In this case, it's this one. And add it to a total. And then the total should be some number, which we will return. We got 4,924. And if I can run the program, do we get the same thing? We got 4,924. So it works perfectly. This was the part 1. And to talk about a bit about the time complexity real quick. There's U, number of pages of updates. There's P, pages per update, and then R, number of rules. And then if we want to just count an N, then we can just assume that N is the number of rules plus the pages and updates, since this is how many things are in the input file. So the time complexity in this case would be, for the parse rules, it would be O of R, so the number of rules, or O of N. The parse updates would be O of U times P, and so on and so forth. But in conclusion, if we want to just use ends, then it's just time complexity of O of N. And the space complexity, since we don't use any crazy for loops to keep storing information, then it's just O of N to just store sort of everything. So it's not too bad for this one. Now, for part 2, if you scroll down a little bit, it seems to be a little bit more complicated, and we're going to use a topological sort to solve it, actually, because what they want us to do now is they want us to find the incorrectly ordered ones. So now we found the correct ones. Now we have to find the incorrect ones. What do we do with them? We have to reorder them so that they are correct based on the rules. So we assume that, okay, the elves or whoever wrote these somehow made a mistake somewhere, and then whoops, we said that we want to print them in the wrong way, but the rules are 100% accurate. So instead of changing the rules, we say, okay, these are the pages that we want to print. We don't know if they're in the right order, but please print all of these. That's what they're asking us to do. So this number would become this thing, and we can see that it's reordered a bit. And instead of 1319 here, it's 2913 because of all of the rules that we saw before. And there's a lot of rules and a lot of things that we need to think about. So the easiest way to do this would be with a topological sort. So if we think about each rule that we get, so each line over here, if it says 97 to 25, 97 to 13, then we would make a node that is 97, and then that points to two different numbers, the 25 and the 13. So in this case, one points to the 2, one points to the 3, and we can see that there is an unsorted graph. So if we would sort of just write this with a piece of paper, on a piece of paper, then this is what we would get. But this is in 2 dimensions. What we want to do is somehow store this in an array in 1 dimension, and then somehow we have to store what points to what. And the way that we do this is in the reorder updates. So that is one way that we could solve it. So for part 2, we're using basically the exact same part. So we're using this part, we're using the parse function, and then I'm calling the solve part 2, which checks, okay, for each update, is it valid? If it's valid, then we don't actually want it in this case. So if it's not valid, then we start to reorder the update. So I made a function reorder the update, and we get the middle index after it's reordered. And that is what they want us to do. We do the exact same thing, but we get a new middle index right after we've reordered it, and then we add this to the total, and then we return that. So and we add this to the total, of course, and we print it. So the main part of this program is just a reorder update, which can be a bit confusing. So I'm using a default dict because it doesn't need a default key. So if you don't give it any key, it still creates that part in the dictionary, but it has a default key. And then also I am using DQ, which is which stands for double-ended queue. And the reason that we use a double-ended queue is since we're going to pop a lot from the first index. So if we have a queue here that's in a normal array, let's say, if we want to remove this part of the index, but there's data here, there's data here, there's data here, okay, there's a problem, because now there's no data here, but we will have to shift all the data over by 1 to be able to sort of not leave any gaps, right? So this is a problem because this takes O of n time complexity, and it's a huge headache. And instead, what we can do is, okay, if we remove this, then what we can do is, okay, we just keep this part, right? So we remove this, and the way that we can do this, there's a lot of different structures for this, but the double-ended queue works for this. We could also use a what did I write here? A circular queue. So a circular queue would be, okay, a queue that just sort of points to itself if you know how big it is, and then the array slots are sort of like this. So if this one gets removed, then the new beginning is here. If this one gets removed, the new beginning is here, and then it just keeps circulating around itself. And the last thing that we could use is a linked list. So we use, different numbers. So let's say 2, 7, 9, and then they point to each other. And then if we remove this, then the pointer from this one just goes to that one. So we have no problem with gaps and stuff. But it's just a bit too complicated for this use case. It's not really necessary. And I mean, we get O of 1 complexity anyway with the DQ. So we will make a graph and an in degree. So as I've said in the topological sort, if we want to make it from 2 dimensions over here to 1 dimension, we will have to make sort of store the information somehow. So we will sort it. We will store it in a graph, which will just be the rules basically. So the graph will just be the graph will just be the x and y coordinates, x and y, and a lot of x and y's, of course. It will store all of the x and y's, and then the in degree is how many incoming edges there are. So if we draw this in 2 dimensions, let's say there's number 2, 3, and 5, and 2 points to 3, 2 points to 5, and then 3 points to 5, right? So the way that we can write this is, okay, we will write that 2 points to 3, so 2 wants to go to 3. This is in the graph, right? And then we will write that also in the graph 2 wants to go to 5, so 2 should be before 5, and then also that 3 is before 5. And one more thing that we write in the what did I name it? And the in degree is how many things are pointing to one thing. So the 2 is pointing to the 3, so there's one thing pointed at the 3. So the 3, one thing is pointing to it, and then the number 2, 0 things are pointing to it, right? And then the number 5, 2 things are pointing to it. It's the number 3 and the number 2 that are pointing to it. There's 2 lines to it. So what we want to do now is that we have these things here, is we iterate over it and we look, okay, which one has 0 things pointing to it? That means that it can be the first thing to be selected. Then we select it, we remove it, and we remove its neighbors. So we remove these lines here, remove this, and remove this. When we remove these 2, what does this mean? We have to update the 3. So now the 3 doesn't have anything pointing to it. We make this into a 0, or we do a -1. And then the 5 doesn't have anything pointing into it anymore, or not the 2 anymore. So we do a -1 as well. So this should become a 1 instead. This becomes a 1 here. And now they are, let's see, this became a 0. And this became a 1. So we iterate again over it, and we see, okay, which one is a 0? Okay, remove it. Which one is a 1? Okay, we can't remove that. So we remove the 0, and then this becomes a 0, and then remove this, and then, okay, we've fixed the entire list. So now it is all ordered as it should be. And there is some problems that we could have with this. So if the data that we got is not, what was the name of it? Is not a cyclical directed, if it is a cyclical directed graph, which means that, okay, if the nodes are like this, so let's say we have 4 nodes, and this points to this, this points to this, this points to this, this points to this, there's a problem. How are we going to start here if this one says it's pointing to it, so it should be first, but this one points to it, but this one points to it, but this one points to it. So it's a sort of infinity loop of, okay, nobody can start first. So what we have to have is not a cyclical directed graph, but rather what are they called? A directed acyclic graph. That's what they're called. So we have to have them not point to each other in a circle. And I mean, they didn't tell us this in the question or anything, but we just have to assume that it is like that, because otherwise there's no way to solve this without having several answers or no answers. So once we do this, we can get a different amount of things that point to each other. So if we sort these, so if we just put them like this, then there's different amounts of pointers that they can have to each other. The minimum amount is n. So if there is n amount, then n minus 1, my bad. Then there has to be at least n minus 1 pointers to each other. So the other problem is that, okay, what if we don't have enough rules actually? What if we have like, okay, we want to get this many pages, but there's only these 3 rules. It is not enough information to know which one comes before the other one. We would have several solutions, which means there's several middle numbers, which means we can't get the same answer every time. So that's a problem. But they did give us 1,100 lines of rules. So apparently that was enough. So at the minimum, it has to be n minus 1 rules if they perfectly point to each other, all the numbers. And at most, it's going to be if each one of them points to all of them. So if this one points to that one, if this one points to this one as well, whoops, it already points there. If this one points to this one as well, if this one points to this one, if this one points to this one. So if all of them point to each other, then it would be just n minus 1 plus n minus 2 plus blah 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 plus 2 plus 1, and then that's how many it would be. And I think it averages out to n over n divided by 2. Should be something like that. But it's a lot of graph combinations. So worst case, this is how many times we would have to iterate through this, and this will come later in the time complexity. So now that we have the graph and that we have the in degrees, we can start, we dequeue it, because every time that we iterate, we have to reset it. So for node in update, we will just add a node that starts with 0. So we've made the entire the entire graph with in degrees, so we have to select one that starts with 0. If there are several ones, then there's several solutions, but we just hope that there's only one, because I don't know, I guess that's how they've structured it, so that there is only one solution, and that's a good way to structure a problem. And then while there is something in the queue, so because we just found the 0, then we keep finding, then we pop it and we add it to the sorted order, and then we try to find another one that has 0, right? After we decrease the degrees of the neighbors. So that's why we have the list of all the neighbors, so that we can decrease it later once we remove a certain node. It's good to think about this in terms of nodes and neighbors. And then we try to find another one, and of course we have to assume that there's more neighbors that have 0. Otherwise, yeah, this wouldn't work. So we just assume that there's always a solution somehow. So then we return the sorted order. So this is the new way that we should sort it. And once we return it in the reorder update function, we will get the sorted order. We will get the middle index again. We will add it to the incorrect total, and then we will print it as a result. So if we run this, we should get 6085, and that is the same thing that it says here, if I'm not mistaken. So a good way to solve this is with the topological sort. It's a bit confusing, and you have to use dictionaries and queues, and it can be inefficient. But the way that I've done it is I've solved it like this, and here's some details about the time complexity. So it's quite bad about the rule validation. It's n squared if you want to say it in n terms, but that's in the worst case scenario. If the graph is not too dense, then it would be O of n, so that's not that bad. So that was today's challenge. It took a lot longer than expected. They keep getting harder every day, it seems. And if anyone wants to join our private leaderboard, I will leave the code in the comments. And yeah, see you guys tomorrow, and happy holidays.